we have a gaseous stream of pure methane. So here is CH4. And a stream of pure oxygen, O2, separate streams. And both of these streams are at 298 and 1 atm. 298, 1 atm. So this device has two bottles sitting there. One is a pure methane bottle and one is a pure oxygen bottle. And they feed this device. And it's coming into the device 298 Kelvin, 1 atm for both the streams. It's a fuel cell. Okay, well, what's a fuel cell do? It's a black box that's going to produce some power for us. Okay, you could read more about fuel cells, but it undergoes a chemical reaction inside such that streams of carbon dioxide, CO2, and a stream of H2O LIQ, liquid water, exit at what temperature? 298 Kelvin for the CO2 and 1 atm. At 298 Kelvin for the liquid water at 1 atm. Can you have liquid water exit at 1 atm? 298 Kelvin? Yes. Yeah, you can. It's possible. So that's a black box for a fuel cell. The fuel cell operates isothermally at 298. So anywhere around here, the surface TB is equal to 298 Kelvin. Okay. The surface of the black box called the fuel cell is 298 Kelvin. Determine the maximum theoretical work that the fuel cell can develop in kilojoules per kilomole of methane. So this fuel cell can produce some, what I'm going to say is a W dot out of the control volume. And its form would be electrical, which is equivalent to mechanical. Okay, it carries with it no entropy, but it sure does carry with it energy. It's a power, mechanical or electrical power coming out of the fuel cell. And they want to know the maximum theoretical work in its per kilomole of methane. So what they want to know is W dot, maybe I put it up here, W dot out of the control volume, electric power, electric work, divided by N dot of the fuel. So if you have a dot dot, you need a dot dot there, right? So this is power over flow rate. Or WCV divided by N, where you get rid of the per unit time on both of them. This would be kilojoules per second divided by kilomole per second. You get rid of the seconds on both of them and you get the desired units, kilojoules per kilomole of fuel. True? Do we know what we were trying to calculate? Now the question is, how do I determine this maximum theoretical work? When you see maximum theoretical work, that's what goes off in your mind. What's going off in your mind is you're going to have to consider the second law of thermodynamics as well. And you're not going to have any irreversibilities. No irreversibilities. So sigma dot's 0. Sigma dot's 0. So does that mean I'm going to do this? Can I still have a Q dot for this fuel cell? They didn't rule anything out about Q dot for a fuel cell, and yes, it will be non-zero. So we need to consider that. You said we have a boundary temperature of 298, but that doesn't mean there's not a transfer of heat across that boundary temperature. Did it say anywhere that the fuel cell's adiabatic? If they would have said adiabatic, we would have said Q dot 0, hence no entropy transfer with the heat. But they didn't ever say that. And so what we have to do is we have to go slowly and we apply the first law. Once we have the first law of thermodynamics applied to this reacting system, then we can apply the second law to this reacting system. What's the equation for the first law look like? Q dot in minus W dot CV out. I'm going to just get rid of this. Just Q dot minus W dot CV. Okay. We're going to do steady state. And then we're going to have the sum of the molar flow rates times the molar enthalpies of all of the reactants minus the sum of the products molar flow rate enthalpies. True? I like to go with ins and outs. Q dots in, W dots out. Sum of the reactants in, products out. So there's a minus sign in front of there. What we can do is write it this way. W dot CV minus Q dot, or put it like this. Q dot minus W dot CV is equal to the sum over the products of N H bar, and I'm going to put this over N dot fuel equal to N times H bar minus the sum over the reactants N H bar. All right, I'm trying to do a couple steps in algebra at the same time. Does that work for you? I guess I better write out my reaction equation. So let's go ahead and tuck that in somewhere up here. CH4 plus some amount of O2 goes to CO2. How many CO2s? 1. And then how many waters? H2Os. Count up the oxygen on that right-hand side. Finish it out. And we have no nitrogen to worry about. So we have the stoichiometric coefficient for the CO2, which is 1, times enthalpy formation of CO2 plus delta H bar for the CO2. Well, the change in enthalpy from the reference state, it's coming out at 298. So isn't that 0? So let's continue with this equation. Plus, for the product, 2 times enthalpy of formation plus delta H bar. It's coming out at 298. But this is H2O It's liquid, liquid, liquid. It has a different enthalpy of formation than vapor. So be careful on that one. Minus, and then we're going to have 1 times the enthalpy formation for the methane, CH4, and the delta H. I should just get rid of all the delta H's because they're all 0. Everything comes in at 298 and goes out at 298. True? So let's dispense with that. Minus how many O2s? 2 enthalpy formation of O2 gas. So we have 3 gas streams, CO2, CH4, O2, 1 liquid stream, water, H2O. At this point, I don't know what Q dot over N dot is. It could be non-zero. It probably is not equal to 0. And I'm really interested in this term, W dot CV over N dot F. That's the term I'm interested in. Isn't that what I want to compute? My answer? So really I have everything on the right-hand side of this equation is determinable. I go get the HF's enthalpy of formations. I get the whole right-hand side computed. But I have 2 unknowns on the left-hand side. I go to the second law of thermodynamics. For a reacting system, ooh, this is going to hurt, right? But it's steady state. And what do we have as an in? Q dot divided by TB. That's a 1 transfer in, right? The directions of both of these Q dots are consistent in the first law as well as in the second law, right? Then we're going to have an in with the reactants. So we're going to sum N dot, and then we'll put S bar naught for each of those reactants, minus the sum of N dot, S bar naught, of each of the products, plus sigma dot. If we want the maximum, theoretical, my guess is sigma dot needs to be 0. It can't be negative. If it's positive, what you would do is you would actually find it. You would calculate that it reduces work or power. So we suspect that that's equal to 0 for a maximum. Okay? So let's expand this equation. I'm going to have to scroll down because there's just a lot to write. Is that okay? Yeah, let's go ahead and do that. So we're going to have the Q dot divided by N dot F divided by TB plus the sum of the coefficient S bar naught. And what I'm going to do is I'm going to say for the reactant CH4 plus N S bar naught for the reactant O2 minus N S bar naught for the product CO2 minus N S bar naught. For the product H2O liquid. True? Did I get that right? All right. This is equal to 0. All right. So what you do is let me draw it. Let me just try not do too much algebra here. But what is it? Q dot divided by N dot F divided by TB. Okay. What is the coefficient in front of CH4? 1. What is S bar naught for CH4? Well, it's going to be S bar naught at the temperature that it comes in at. The temperature that it comes in at is 298, isn't it? Minus R bar, natural log, the mole fraction of that stream that it comes in at, times the pressure of that stream that it comes in at, divided by 1 atm. That's our reference pressure. I stop, I pause. Does that look good? It's pure stream of CH4 methane coming in. So what's Y for that pure stream? What's the mole fraction of methane in a pure stream of methane? 1. And it's at 1 atm. So guess what? This is 1, this is 1, all that's 1. Natural log of 1 is 0. So this whole part goes to 0. So all you're left with is the value of the absolute entropy at 298, and I can get out of either, well, I get it out of the table. Okay. This is for the methane, CH4. You do the same thing for the oxygen. How many oxygens were there? 2. And then you'll have S bar naught of the oxygen at 298 minus R bar natural log of Y of the oxygen, pressure is a stream that the oxygen's coming in at, and then 1 atm for the reference. Same discussion. This is 1, this is 1, that's 1. Natural log of 1 is all 0. Boom. So you're just left with that one remaining term. So those are the two for the reactants. Let's take a look at the products. Minus CO2. How many CO2s? I have to scroll back up. I forgot myself. 1 CO2? Yes, and then 2 waters. So 1 CO2, S bar naught 298. And it's pure CO2 coming out. So even though there's a minus R bar natural log, that all goes to 0 for the CO2. Then we had 2 times the S bar naught at 298. Now, it's not coming out as a gas, all right? So this is where it's a liquid. That's where we end right there, okay? We end right there for the liquid H2O LIQ. So we just get the value of S bar naught out of the table for H2O liquid. And it's in the table. Remember, it's right below the vapor. Should I jump back and see if I have that table? Let me see if I have that table. Okay, I have the gas, but right below it's the liquid. And there's an S bar. Maybe it's there it is. It's 69.95. Don't use the 188.72. There's a difference, true? That one's for the liquid, so that's the one we want. Okay. So at this point, take a look. Can I get this S? This S? This S? That S? Yes. Do we know TB? You know TB. And so you can actually calculate that ratio, Q dot over N dot F, to ensure that the second law is satisfied. True? So you can solve for Q dot over N dot F. The second thing you can do is go back now to the first law. And that first law is, this is now determined, right? So bring that over to the other side of the equation. You only have one unknown. You can solve for W dot over N dot F. That's our answer. That's what we wanted to do. Now you probably, I have to grab a bunch of numbers and put them in there, but let me show you a little bit of how I did this in Excel. All right. And so if you're looking for, let me just outline it for you. This right here is describing that methane coming into a fuel cell. And there's no nitrogens. There's no oxygen going out. But there is 2 H2Os going out, 1 CO2 going out for 1 methane and 2 oxygens coming in. So those are my N's. And I just recycling a previous spreadsheet. So I could change this, but this is, I usually do theoretical and then excess error. But, so that's why it's that doubled up. Now, coming in, we have methane, and I have to get enthalpy of formation. And I have to get S naught out of the tables for that methane. With the enthalpy of formation and the oxygen and everything, I can get the sum over all of the reactants of the coefficient times the enthalpy of formation. There's only really one term for the methane. That's in the energy. Likewise, CO2 going out, we type in its enthalpy of formation, and we know the stoichiometric coefficient, and there's no delta H. Delta H is 0, so we get the coefficient times H of F for the CO2. You do the same thing for H2O, but notice it's liquid, so I need to put in a liquid's enthalpy of formation, as well as over here I'm going to do entropy calculations in this zone. Right here, I'm doing energy calculations, okay? Whatever. Okay, let me escape here. So then I do the sum over all of the products for the energy. Okay. Now, let's take a look at the entropy calculations. I have to scoot a little bit here. We get the mole fractions of the methane coming in its own stream and the mole fraction of the oxygen coming in its own stream. And we have S naught and S naught. And so you can get N times S's, sum them up for all of the reactants. Likewise, the N times the S's, notice you need that S naught for the liquid water. You get the sum of the S's over all of the products. True? Okay. At this point, I did it slightly differently, but we can definitely do it this way. Let me turn this around. What was our equation that we just developed for calculating Q dot divided by N dot F? Wasn't that equal to the sum of this one minus this one? I need to put a parenthesis there. And then we had to multiply by the 298 because the TB came up. True? And look at that. I did it slightly different, another way, but there I just did it, and they're consistent. Okay? So now I have the Q dot divided by N dot F. From the energy balance, the work minus the Q minus the work divided by NF is this. That just comes from this 2 difference. Okay? And so if I wanted to, I could calculate the work knowing that it's equal to minus this plus this. I just went back to the first law. Everything on the right-hand side was calculated, the sum of the products, sum of the reactants, and then brought over to Q, and so there it is. So that's our answer. So it's 818,023. All right. Now, what I had done earlier, though, was I had used a different technique, and I had calculated down here the term in the second law, Q dot over TB. So it's entropy transfer into the control volume with heat transfer for kilomole of fuel. You can see I explain it right there. The sum of the reactants right there. This is the sum of the products right there, just bringing it down. See that? Escape. Okay, and then what I had done was this is a sigma dot, and I would calculate the sigma dot from an entropy balance, and I would guess, maybe I guessed it was 50,000. Okay, well, if it was 50,000, then my sigma dot's not 0. So in Excel, once you get used to Excel, you like the feature under data. So under the data tab, what if? Go to goal seek. I didn't name this thing. It should be like root finder or something like that. Okay, and it says take that cell, which is C25. I want to set it to make it go to a value of 0 by iteratively changing this one, and then there it is. Click OK. Let's say that somebody said, no, I think it's 900, 1, 2, 3, something like that. Well, you have a negative sigma dot. Impossible. Violates the second law of thermodynamics. Somebody says, no, I don't have that. I have whatever, 700. Well, you have a positive sigma dot, meaning there's some irreversibilities occurring. The maximum work you can get out of that fuel cell is 818,023. And sigma dot's equal to 0. So it's reversible.